Hi everyone, in this video we are going to learn about system of coaxial circles and we are going to see how to determine the equation of such a system of circles. First, let's take a look at the definition. The definition goes like this: in a family of circles or in a system of circles, if each pair of circles have the same radical axis, then the system of circles is called the system of coaxial circles. It is such a system of circles where any two circles have the same radical axis. You can pick any two circles from such a system and their radical axis would be the same straight line. Let's see a few examples. Here is an example where I have presented 6 circles and you can pick any two of these 6 circles. Their radical axis is the same straight line, which is the yellow dotted line here. That is the radical axis. Let's take a look at another example. Here again I have presented 6 circles and the radical axis, and as you see the circles actually touch each other, and if you pick any two circles from this system, the radical axis would be the same yellow dotted line. Let's also take a look at another example. Here I have another example where the circles don't intersect or touch, and here again I have presented 6 circles and also the radical axis, and you can pick any two circles from this system. The radical axis will be the same yellow dotted line, and this type of a system of circles would be called a system of coaxial circles. Next we are going to see how to determine the equation of such a system of coaxial circles. As in the first example, we had the circles intersecting each other and the radical axis is actually the common chord. In the second case, the circles touch each other and there the radical axis is nothing but the common tangent. And in the third example, the circles neither touch nor intersect. To determine the equation of such a system of coaxial circles, we need at least the equation of 2 circles from the family or the equation of a circle and the equation of the radical axis. So let's take the situation where we have been provided with the equation of 1 circle from such a family and also we have been provided with the equation of the radical axis. Then what would be the equation of this system of coaxial circles? It will be kind of like this: S plus some real number k times L. Now what is S? Well, S is the left hand side of the equation of the given circle and L is the left hand side of the equation of the radical axis. In this case, the equation of the system of coaxial circles can be written as S plus some real number k times L equals 0, and k can be any real number. Let's take a look at the first 2 examples again. There you will notice that the family of circles would actually pass through the points of intersection of a circle and the given radical axis. That means this is similar to the equation of the family of circles passing through the points of intersection of a circle and a straight line. If the straight line is the radical axis, then we can assume that this family is nothing but the family of circles passing through the points of intersection of a circle and a straight line. I have already created a separate video on this topic. I have shared the link in the description. Feel free to watch that video, and there I have explained in details how to derive the equation of such a family of circles. Here we are also going to try to prove it in a different way, but I am not going to repeat the same steps that I have done in the previous videos whose links have been shared in the description. Here we are going to do the proof in a slightly different way. Now let's see how we can prove it. So here we are going to see how we can prove that the equation of the family of coaxial circles will be like this when we are provided with the equation of 1 circle of that family and the equation of the radical axis. As we just saw, that equation would be S plus some real number k times L equals 0, where S is the left hand side of the equation of the given circle from the family and L is the left hand side of the equation of the radical axis. And from this family, let's take 2 sample equations. One equation can be written like this, where we are taking some specific value of k. I have denoted that as k sub 1, and let's consider that this is the equation of one of the circles from this family. And then I'm going to take another equation which looks like this, and let's consider that this is a second circle from the same family. And here I am using a different value for k, so I have denoted that as k sub 2, and let's assume that k sub 1 and k sub 2 are not equal, they are just different real numbers. I have taken 2 distinct circles equations from the family. Now in the previous video I have also explained how to derive the equation of radical axis, and we know that the equation of radical axis can be written like this: s sub 1 minus s sub 2 equals 0. And then let's plug in the values. So we can write the equation of the radical axis like this, and if we remove the parenthesis then it can be written like this. As you see, we have the positive s and the negative s, they will cancel out each other, and we are going to be left with something like this. Since k sub 1 and k sub 2 are different numbers, then k sub 1 minus k sub 2 is not equal to 0, and so let's divide both sides of this equation by k sub 1 minus k sub 2, and if we do that we can write our equation like this. And as you see, we started with the assumption that L equals 0 was the equation of the radical axis of the circles of this family, and finally also by taking two random circles equations from the family, we are able to prove that in fact the equation of the radical axis of those two circles is L equals 0. So this is sufficient to say that s plus k times L equals 0 actually represents the family of the coaxial circles. Also, this equation of the system of coaxial circles can be written like this, and from here we can write it like this, and from here we can write it like this, and this looks like the equation of a circle. So as you can see that s plus k times L equals 0 actually represents a bunch of circles where k is the parameter. By changing the value of k, we can come up with infinite number of circles, and all of that will belong to the same system of coaxial circles. Next, we are going to take a look at another flavor for the equation of the system of coaxial circles. If we are provided with the equations of two circles from a family of coaxial circles, let's suppose we have been provided with these two equations, then we can say that the equation of the system of coaxial circles can be written as s sub 1 plus some real number k times s sub 2 equals 0. Here k is a real number and k cannot be negative 1. I will explain in a few seconds why k cannot be negative 1, but for a moment let's assume that k cannot be negative 1. Now if we plug in the values of s sub 1 and s sub 2 in this general form, then we can write the equation like this, and from there if we remove the parenthesis then we can write the equation like this, and then we can write the equation like this, and then to make the coefficient of the x squared term and the y squared term, we can divide both sides of this equation by 1 plus k. Since we have assumed that k is not negative 1, we can easily divide by 1 plus k, and now it looks like the equation of a circle. And here as you see in the denominator we have 1 plus k, so denominator can never be 0, that means 1 plus k cannot be 0, that means k cannot be negative 1. Now what happens if k is negative 1? Well, if you look at the previous line where you see the coefficient of the x squared term is 1 plus k, now if we take k as negative 1, then the coefficient of x squared term becomes 0, similarly the coefficient of the y squared term also becomes 0, that means it will not be the equation of a circle, it will become a linear equation, it will become the equation of a straight line. So to make it look like the equation of a circle, we have to avoid negative 1 for the value of k. We can take any other real number for the value of k except negative 1. Now here is another flavor of this equation of the system of coaxial circles, because if you imagine s sub 1 minus s sub 2 will represent the left hand side of the equation of the radical axis, and then as we saw just a few minutes ago, s sub 1 plus k times L equals 0, that is the general equation of the system of coaxial circles. Here also we can write it like this, that s sub 1 plus some real number k times s sub 1 minus s sub 2 equals 0. This is similar to s sub 1 plus some k times L equals 0. We are now going to review an indirect proof of the fact that s sub 1 plus k times s sub 2 equals 0 in fact would represent the equation of the system of coaxial circles. So let's take a look at that proof. So here we need to prove that if we are provided with the equations of two circles from a family of coaxial circles, we can say that the equation of the family of coaxial circles can be written in general as s sub 1 plus k times s sub 2 equals 0, where k is any real number other than negative 1. Now in order to do the proof, again we are going to take two sample circles from this family. Let's suppose the first sample circle's equation is s sub 1 plus some real number k sub 1 times s sub 2 equals 0. And let's suppose that the equation of the second sample circle that I am taking can be written as s sub 1 plus some real number k sub 2 times s sub 2 equals 0. Here again k sub 1 and k sub 2, they are not equal, and also each of them not equal to negative 1. Now if you look at each of these equations of the sample circles, you will realize that the coefficient of the x squared term and the coefficient of the y squared term is going to look like this. Let's consider the first circle. There the coefficient of the x squared term and the y squared term will look like 1 plus k sub 1. Similarly, on the second one, the coefficient of the x squared term and the y squared term will look like 1 plus k sub 2. Now, to make the coefficient as 1, we should divide this equation by 1 plus k sub 1 or 1 plus k sub 2 to make the coefficient of the x squared term and the y squared term as 1. So I have divided the first equation by 1 plus k sub 1. This is just to make sure that the coefficients of the x squared term and the y squared term become 1. And I'm going to call it s sub 3 equals 0. Similarly, for the second sample circle, I divided the equation by 1 plus k sub 2. Actually, I am dividing on both sides. 0 over 1 plus k sub 2 is nothing but 0. Similarly, on the first example also 0 over 1 plus k sub 1 is nothing but 0. So please assume that I am dividing both sides of each of those equations. Now let's call the second sample circle's equation as s sub 4 equals 0. Now for these two sample circles, what would be the equation of the radical axis? Well, we know that the equation of the radical axis of any two given circles can be written like this. Next, I am going to plug in the values of s sub 3 and s sub 4. So our equation is going to look like this. And then I am going to simplify a little bit. Our equation would look like this. And then I am going to multiply both sides of this equation by the product of 1 plus k sub 1 times 1 plus k sub 2. If we do that, our equation will look like this. Also please note that I have multiplied each of the terms in the numerator there. And in the next step, I am going to get rid of the parenthesis. So our equation would look like this. And then you see we have a positive s sub 1 and a negative s sub 1. They are going to cancel out each other. Similarly, we have the positive k sub 1 times k sub 2 times s sub 2 and the negative k sub 1 times k sub 2 times s sub 2. They are also going to cancel out each other. And finally, we are going to be left with something like this. And from here, we are going to do a little bit of factoring. And finally, our equation could look like this. And because we have assumed that k sub 1 and k sub 2, they are two different values, meaning they are two distinct real numbers. So k sub 2 minus k sub 1 can never be 0. And we can safely divide both sides of this equation by k sub 2 minus k sub 1. And if we do that, the left hand side will become s sub 1 minus s sub 2 and the right hand side will become 0 over k sub 2 minus k sub 1, which is nothing but 0. So our equation going to look like this. And as you can see, this is representing the radical axis of the two sample circles that we started with. So here I have noted that using the equations of any two circles from this family or system, we find that the radical axis has the equation s sub 1 minus s sub 2 equals 0. And that concludes the proof. I hope the proof was clear. Next, we are going to take a look at a couple of special cases. Let's talk about the first special case. This is a system of coaxial circles where the centers of all the circles lie on the x-axis and the radical axis is the y-axis. In that case, what would be the general equation of this system of coaxial circles? We know that the general equation of a circle is like this. And in this case, because the centers of all of the circles of this family lie on the x-axis, that means the y-coordinate of the center should be 0. That means f will be 0. And in that case, the general equation of all the circles in this family could look like this. And from here, we can say that the equation would look like this: x squared plus y squared plus 2gx plus c equals 0. Now the question is, how many parameters do we have in this general equation? Looks like there is a g and a c. Are both of them the parameters in this equation? Well, let's try to find that out. Whether we have one parameter or two parameters, let's find that out. If we assume that we have two parameters here, g and c, then let's take two circles using this general equation. Suppose we have taken two circles like this. We are using some two different values of g and two different values of c. Now what would be the equation of their radical axis? Well, we can write it like this. And then if we plug in the values of s sub 1 and s sub 2, the equation will look like this. And if we remove the parenthesis, we can write it like this. And here you see we have positive x squared and negative x squared. They are going to cancel out each other. And similarly, we have positive y squared and negative y squared. They are also going to cancel out each other. And we are going to be left with something like this. So from here, let's see what is the value of x. X can be written like this. So we have arrived at the equation of the radical axis of those two circles, where we know that the radical axis is nothing but the y-axis. That is the assumption that we started with. So in this case, we can say that the x value will be equal to 0 because x equals 0 is the y-axis. So if we assume that this radical axis is nothing but the y-axis, then we can say that it will be x equals 0. That means this particular value should be equal to 0. And from there we can say c sub 2 minus c sub 1 will be equal to 0, which means c sub 2 equals c sub 1. And let's assume that it is some constant c. So it looks like c is not a parameter. Even though we assumed that c could be a parameter and we started with two different values of c, ultimately we see that actually their values have to be equal. So looks like c is not a parameter, it is just a constant. So then we are left with just the g, and in fact yes, g is the parameter, and that is the only parameter in that equation of the system of these coaxial circles. And that is the general equation of the system of these coaxial circles. Next, we are going to do a little more analysis on this general equation. If the circles intersect, the points of intersection will lie on the radical axis. As you have seen in the very first example, the first diagram, there we saw that the points of intersection of those circles would lie on the radical axis, because radical axis is actually same as the common chord, and in this case the radical axis is the y-axis, so we can assume that the points of intersection of the circles will lie on the line x equals 0, which is nothing but the y-axis. So if we take a circle whose equation can be written as x squared plus y squared plus 2 times g sub 1 times x plus c equals 0, we are taking some real value of g, some real number g sub 1, and we can say that this could be one of those equations, and this equation should satisfy x equals 0, because here we assumed that the circles intersect each other, and if that is the case, the points of intersection will lie on the y-axis, which is assumed to be the radical axis for this system. So this equation of one circle of that family should satisfy x equals 0. So we can plug in x as 0 in this equation, and we get y squared equals negative c, and from there we can say y can be written as plus or minus square root of negative c. Now think about the value of c. If c is a negative number, then negative c becomes a positive number, and within the square root, negative c being a positive number is a good thing. That means y will have real and distinct values. That means the circles will in fact intersect each other. Now if c is equal to 0, then y's value also becomes 0. That means the circles will touch each other at the origin. And if c is positive, then negative c becomes negative, then the value of y will become an imaginary value. That means no two circles of this system will touch or intersect each other. I hope things are clear up to this point. Next, we are going to talk about a similar system of coaxial circles where the centers lie on the y-axis and the radical axis is the x-axis. Here again, we are going to begin with the general equation of a circle, and in this case, as we assumed that the centers of the circles lie on the y-axis, that means the x-coordinate of the circle center would be 0, that means g will be equal to 0. And if we use that value of g in this equation, we can write it like this, and from there we get x squared plus y squared plus 2fy plus c equals 0. And again, it seems like there are two parameters, but we can use the same steps as we just did in the previous example. We can finally prove that in fact there is only one parameter in this general equation, and that will be f. C is not a parameter, it's just a constant. Here I have all the same notes. As you can see, using the same steps, we can prove that c sub 2 is equal to c sub 1 for two sample circles, and we can take that as some constant c. So c is actually not a parameter. So we have only one parameter, and that is the f. So the general equation of this system of coaxial circles can be written as x squared plus y squared plus 2fy plus c equals 0, where f is some real number, and the assumption is that the centers of all of the circles lie on the y-axis and the radical axis is the x-axis. Here again, we are going to do a little bit of analysis for the value of c. If we assume that the circles intersect, then the points of intersection will lie on the radical axis, which is nothing but the x-axis. That means the radical axis's equation is y equals 0. Now if we take one of the circles from this family, and let's assume that f sub 1 is some real number, so we can say that the equation of a circle from this family can be written like this, and there I have plugged in the value of y as 0, that is the y coordinate of the points of intersection, and using y equals 0 we are going to get something like this, and from here we can say x is equal to plus or minus square root of negative c. Now if c is a negative number, then negative c is a positive number, then square root of negative c will give us some real values. So when c is negative, x has real and distinct values, which means the circles in fact intersect each other. And then if c is 0, then the value of x becomes 0, that means the circles don't intersect but they touch each other at the origin. And when c is a positive number, negative c becomes a negative number. That means the value of x becomes imaginary. That means no two circles touch or intersect. I hope things are clear up to this point. Finally, we are going to take an example. Let's suppose we have an example like this that says find the equation of the system or family of coaxial circles whose two member circles equations are given as x squared plus y squared plus 8x plus 10y plus 24 equals 0, and the other one is x squared plus y squared minus 10x minus 6y plus 30 equals 0. Also, find the equation of the circle from this family that passes through the origin. So we have to find two things here, right? First, we have to find the general equation of the system of coaxial circles from the two given circles equations, and also we have to find out the equation of a specific circle from this family that passes through the origin. So let's get started with the solution. The two given circles equations can be written like this. And so what would be the general equation of the system of these coaxial circles? Well, it can be written like this: s sub 1 plus some real number k times s sub 2 equals 0, where k is not equal to negative 1. And then if we plug in the values of s sub 1 and s sub 2, the equation would look like this. And that is the general equation of the family of these coaxial circles. The two given circles also belong to the same family, because based on their equation we have come up with the general equation of the family of coaxial circles. Also, it can be written in another form. I have written the steps. You can easily see it. All I have done is I have removed the parenthesis, and then I have tried to make the coefficient of the x squared term and the y squared term as 1. So those are the two different forms of the general equation of this family of coaxial circles. So that is the answer to the first question. Next, we have to find out the equation of a circle from this family that passes through the origin. So if this general equation satisfies all the circles in this family and there is a circle that also passes through the origin, so that circle's equation should also be satisfied by the coordinates of the origin. And in that case, the general equation should satisfy x equals 0 and y equals 0 because the circle passes through the origin. Now, based on this condition, we should be able to find the value of k, and then we will be using that value of k in the general equation to find the actual equation of that circle. So because the given condition is that the specific circle passes through the origin, I am going to use x equals 0 and y equals 0 in the general form. So we can write it like this, and then we just simplify a little bit. We find that k is equal to negative 4 over 5. And now let's use this value of k in the general equation. That should give us the equation of the specific circle that passes through the origin. So the equation of the circle can be written like this. All I have done is I have used that specific value of k in the first form of the general equation of the family of circles. And then we are going to simplify this. Finally, we get the equation of the circle. I have noted the steps here. You can clearly see it. It's pretty easy. Finally, we get the equation of that specific circle that passes through the origin. And that equation is x squared plus y squared plus 80x plus 74y equals 0. And that is the answer to the second question in this example. I hope all the derivations made sense. Thank you for watching. See you in the next video.